Hello students, welcome back to session 4 of linear transformations. So in the last class we have studied what is meant by matrix of linear transformations. So this is, say suppose if T belongs to A of V, means T is a transformation from V into V, and if V1, V2 etc. if V1, V2 etc. is a basis of V, then each of these elements T of V1, T of V2 etc. T of Vn, each of these elements belongs to V, and so they can be written as the linear combination of basis elements. Say T of V1 is equal to say alpha 1 1 V1 plus alpha 1 2 V2 etc. alpha 1n Vn, and T of V2 we can write like this. Likewise T of Vn is alpha n1 V1 plus alpha n2 V2 and so on alpha nn Vn. So if we write the matrix of the coefficients of the above system of equations, say alpha 1 1, alpha 1 2 etc. alpha 1n is alpha 2 1, alpha 2 2 etc. alpha 2n and so on alpha n1, alpha n2 etc. alpha nn. So this matrix of coefficients of the above system of equations is known as the matrix of T. This we already discussed in detail in the previous class itself. Okay. So these set of n square elements will completely determine the nature of T. Okay, as we have discussed, all the properties of a T, the transformation T belongs to E of V, being hidden in this matrix. This is a n cross n matrix. Okay. So now we have discussed that a vector space may have more than one set of basis elements. Say here V1, V2 etc. Vn is a basis. So suppose say I will take W1, W2 etc. Wn as another set of basis elements for the vector space V itself. Okay. Then corresponding to this basis definitely we have some matrix, say that is also matrix of T, say relative to this basis W1, W2 etc. Wn. Say we may denote this by matrix of Mw of T. This is matrix corresponding to the first basis, or M1 of T, better this is the notation. Okay. So M1 of T, M2 of T. So now both of these matrices represents the same linear transformation, which is T. Okay. Now if these both represents the same linear transformation T, and also we have proved the set of matrices or the collection of all homomorphism or linear transformations on V is denoted by E of V. Say this is E of V, and we have shown that E of V is in fact isomorphic to Fn. Okay. So now we have two matrices corresponding to 2 depending on the different set of basis elements. But if you go back, as I said, there is a one-to-one correspondence between the set of matrices and the set of linear transformations. Now for each transformation there is a corresponding matrix, and for each matrix there is a corresponding transformation. Okay. Now if these two M1 of T and M2 of T represents the same linear transformation T, okay, can these gives back the same linear transformation? So let's verify this. Okay. So if M2 of T is the matrix of T, M1 of T is also matrix of T, but with respect to this basis V1, V2 etc. Vn, and this is matrix with corresponding to W1, W2 etc. Wn. So if they give back the same linear transformation, there should be some relation between these two matrices. What is that relation? Okay, that relation we will discuss in this class as a theorem. Okay, say we will discuss this theorem. Suppose V is a vector space of dimension n over a field F and let T belongs to A of V. If M1 of T and M2 of T are the matrices of T relative to two set of bases V1, V2, etc. Vn and W1, W2, etc. Wn of V respectively, then there is an invertible matrix C belongs to Fn, invertible matrix C belongs to Fn such that M2 of T can be written as C into M1 of T into C inverse. You observe this. So the matrix M1 and M2 are related by this relation. M2 of T is equal to C times M1 of T into C inverse, or in other words M1 of T can also be written as some D into M2 of T into D inverse. Okay, one and the same. So let us prove this. Okay, so for this I will define a linear transformation. Say S from V to V be defined by S of Vi is equal to Wi. So S carries every basis vectors Vi to the basis elements Wi. Okay, so S from V to V by S of Vi is equal to Wi. I takes the value from 1 to n. Then certainly we can see that S is a linear transformation or S is linear. Okay, you can verify this. Okay, moreover we can see that this transformation S is onto. S is onto. If you want to show this, say let us take any arbitrary element y belongs to V. Then y can be written as y is equal to say C1 W1, C2 W2, etc. Cn Wn, because y we have taken from the codomain set V. So therefore it is, say I will define by y is equal to C1 W1, C2 W2, etc. Cn Wn, where Ci belongs to F. And using these same scalars we can find that x can be written as C1 V1, C2 V2, etc. Cn Vn. This x certainly is a linear combination of basis elements V1, V2, etc. Vn. So and therefore it belongs to V. And S of x is what? S of C1 V1, C2 V2, etc. Cn Vn. So this is equal to, since S is linear, C1 S of V1, C2 S of V2, etc. Cn S of Vn. That's equal to C1 into S of V1 is what? W1. C2 into S of V2 is W2 and so on. Cn into S of Vn is Wn. So this is C1 W1, C2 W2, etc. Cn Wn is in fact the vector y. Okay. So S of x is equal to y means if we take an y in the codomain set V, then there exists x belongs to V domain set such that S of x is y, therefore S is onto. Now S is onto means we have proved one result. The transformation T belongs to A of V is invertible if and only if S is onto. According to that result, here S is, as S is onto, S is invertible. Now S is invertible means what? S inverse exists. Definitely S inverse exists, and it also is the element of A of B because A of is an algebra. Now look here. So now T of W1 is an element of, look here, T of W1 is an element of V1 because W1, W2, etc. Wn belongs to V means T of W1, T of W2, etc. T of Wn belongs to V, and so each of these elements can be written as a linear combination of basis elements which are W1, W2, etc. Wn. Therefore the general element T of Wi can be written as T of Wi is equal to summation over j Bij into Wj. Now if we yes, this implies what? T of Wi means what? S of Vi. S of Vi is equal to summation over j Bij into Wj. In place of Wj I can write S of Vj, or this implies S into T of Vi. This can be written as S into T of Vi is equal to S of, okay, or here S of summation over j Bij Vj, because S is a linear transformation. So this implies multiplying throughout by S inverse, we get S inverse of S into T of Vi is equal to summation over j Bij Vj, because S inverse into S is I, because S is an invertible transformation. This implies ST S inverse of Vi is equal to summation over j Bij Vj. Now ST S inverse is a transformation. Okay, it is a transformation on V itself. It is an element of A of V. Okay, because S belongs to A of V, T belongs to A of V means S into T belongs to A of V, and ST belongs to A of V and S inverse belongs to A of V means ST S inverse belongs to A of V. Okay, now this is like some transformation. Say if we call this by say some U inverse of Vi is equal to this one, where U is a linear transformation from V to V. Then by the definition of linear transformation relative to the basis, we have matrix of ST S inverse is equal to what? Matrix of ST S inverse, that we may denote it by, since we have written with respect to Vi's, so I written M1 of ST S inverse is equal to, what is the matrix? So Bij is the matrix. But Bij is nothing but the matrix M2 of T. Therefore, matrix M1 of ST S inverse is equal to Bij, that is equal to M2 of T. But we know that the mapping T from mapping which maps every transformation to its matrix is an isomorphism of A of V onto Fn. This we have shown in the last class. Therefore, this is an isomorphism means it is a linear, means homomorphism. Accordingly, M1 of ST S inverse can be written as M1 of S into M1 of T into M1 of S inverse. That's equal to M2 of T. So this is equal to M1 of S into M1 of T into M1 of S inverse can be written as M1 of S whole inverse, because matrix of a inverse of a linear transformation is nothing but the inverse of the matrix of that transformation. Okay. Accordingly, this is equal to M2 of T. You call this M1 of S by C. C into M1 of T into C inverse is equal to M2 of T. Okay, where C is M1 of S, which is an element of Fn, means n plus n matrix is invertible. Thus, the relation between M1 of T and M2 of T is M2 of T is equal to C into M1 of T into C inverse, where C is the matrix. C is the matrix of S. What is S? S is a mapping from which maps? S is mapping from V to V, which maps S of Vi is equal to what? Wi. So what it is doing? It is changing the basis Vi to Wi. So we can call this S as the transformation of change of basis, and therefore the matrix C corresponding to S, the matrix C corresponding to S is called the matrix of change of basis. Here C is called the matrix of change of basis. Okay. So now let's verify this theorem by taking particular examples. Say first I will take example of this type. Say look here. Suppose we have a vector space R3, V is equal to R3, and suppose we have a transformation T belongs to A of V. Given M1 of T, matrix of T is equal to 1 1 2 minus 1 2 1 0 1 3 in the standard basis. Standard basis, what is the standard basis of R3? The standard basis is 1 0 0, V1 is equal to 1 0 0, V2 is equal to 0 1 0, V3 is equal to 0 0 1. These are the standard basis. Now we need to find the matrix of T in the following set of basis elements. So first set of basis elements I have taken to be 1 1 1, 0 1 1, 0 0 1. The next set of basis elements is 1 1 0, 1 2 0, 1 2 1. So see here, it's here from this example it can be seen that there are three different set of basis elements for R3, but note that all the basis contains the same number of elements, which is 3. Okay. Likewise, there may be more than 3 sets or any number of basis elements for a vector space. Okay. So now let us find the matrix of T. Here they were given. So let's find the matrix of T in the new basis U1, U2, U3. So to find the matrix of T related to the basis U1, U2, U3, first we need to find, as I said, first we need to find how the transformation looks. So they were given the matrix of some transformation which is T. So we need to know how the transformation itself looks. Okay, that's a big task, as I said. So finding the matrix is easy. but corresponding to, if you know the basis, we can find it the matrix of T easily. We have taken such example in the previous class. But going back from matrices to linear transformation is little bit a tougher task. So let us do that also in this class. Say, right, first let us find the linear transformation T. If you find the linear, if you know how the transformation looks, then it will be very easy to find the matrix of the transformation in the new set of basis elements, okay, which is 1 1 0 0 1 1 0 0 1. Say, let's find this transformation. So they were given, say the matrix M1 of T, they were given like 1 1 2 means what in the standard basis means what. This is the row corresponding to, this is the coefficients like alpha 1 1, alpha 1 2, alpha 1 3 in the standard expression. So T of V1 is equal to alpha 1 1 V1, alpha 1 2 V2, alpha 1 3 V3. Okay. So now according to that, T of V1 is what? T of 1 0 0 V1 is 1 into standard basis. This can be written as a linear combination of basis elements. These are the matrix, means they are the coefficients Ci's or alpha i's. Therefore this can be written as 1 into 1 0 0. Okay, answer now 1 into 1 0 0 and 1 into 0 1 0, 2 into 0 0 1. Where this comes? These are 1 into 1 0 0, 1 into V1, 1 into V2, 2 into 1 into V1, 1 into V2, 2 into V3. So like 1 into V1, 1 into V2, 2 into V3. Similarly, T of V2 is what? T of 0 1 0. 0 1 0 can be written as, the coefficients are minus 1 2 1. So minus 1 into 1 0 0, 2 into 0 0 0 1 0, okay, plus 1 into 0 0 1. Okay, this is equal to minus 1 into V1 plus 2 into V2 plus 1 into V3. Next, T of V3. T of V3 is what? T of 0 0 1. T of 0 0 1 is what? Again 0 into 1 0 0 plus 1 into 0 1 0 plus 3 into 0 0 1. So this can be written as 0 into V1 plus 1 into V2 plus 3 into V3. So we got three equations. T of V1 in the as linear combination of V1 V2 V3, T of V2 as a linear combination of V1 V2 V3, T of V3 as a linear combination of V1 V2 V3. Now any element V belongs to V implies how V looks. So V look like, so the linear combination, say alpha 1 V1, alpha 2 V2, etc. alpha 3 V3. This implies T of V is equal to what? T of V is T of alpha 1 V1, alpha 2 V2 plus alpha 3 V3. So this is equal to alpha 1 times, since T is linear, this can be written as alpha 1 times T of V1 plus alpha 2 times T of V2 plus alpha 3 times T of V3. So alpha 1 into, this is equal to alpha 1 times, what is T of V1? T of V1 is what? So this is V1 plus V2 plus 2 V3. So I write V1 plus V2 plus 2 V3 plus alpha 2 times T of V2, you write minus V1 plus 2 V2 plus V3, and alpha 3 is 0 V1 plus V2 plus 3 V3. So now you collect all the coefficients of V1, V2, V3 in this expression. You get like, say alpha 1 minus alpha 2 plus 0 alpha 3 means alpha minus alpha 1 minus alpha 2 into V1 plus next coefficients of V2, alpha 1 plus 2 alpha 2 plus alpha 3 into V2. Next coefficients of V3. V3 is 2 times alpha 1 plus alpha 2 plus 3 times alpha 3 into V3. Therefore transformation T is what? T of alpha 1, alpha 2, alpha 3 is nothing but the coefficients alpha 1 minus alpha 2 is alpha 1 plus 2 alpha 2 plus alpha 3, and third coordinate is 2 alpha 1 plus alpha 2 plus 3 alpha 3. So we find the linear transformation T. So this is the transformation T, and the matrix they were given with the standard basis. You can cross verify it. So if you put say 1 0 0, what you get? First row of the matrix. 0 1 0 if you put, then you get the second row of the matrix. you get 0, 0, 1, then you will get the third row of the given matrix. So this transformation represents is related to the matrix which they were given, or the matrix which they were given, this one 1 1 2 minus 1 2 1 0 1 3 is the matrix corresponding to the transformation obtained now. Okay, so this is the transformation. Now once we know the transformation, then it is easy to find the matrix of any transformation with respect to the next set of basis elements. The next set of basis elements, they were given to be 1 1 1 0 1 1 0 0 1. Okay, so let's find this. Now T of u1, T of u1 is what? 1 1 1. T of 1 1 1 is according to this. 1 1 1 means 1 minus 1 0. Yes, 1 plus 2, 2 times 1 plus 1 means what? 2 plus 2 4. Next 1 1 is 2 1 is answer now 2 plus 1 3 plus 3, it is 6. So look here, T of u1 is equal to 0 4 6. Now if u1 u2 etc. un, these elements belongs to V because they are the basis elements, they are the elements of V. If they belongs to V, then T is a mapping from V to V. Therefore T of u1, T of u2, T of u3 are also elements of V only. Okay, so if they are elements of V means each one can be written as a linear combination of basis elements. Which are the basis elements? These are the basis elements. So 0 4 6 can be written as, say, beta 1 times 1 1 1 plus beta 2 times 0 1 1 plus beta 3 times 0 0 1. So this implies this is equal to what? First is beta 1, beta 2 0, beta 3 0, first coordinate. Next is beta 1 plus beta 2 0. Okay, next beta 1, beta 2, beta 3. Therefore you equate on both the sides. What do you get? So 0 4 6 is equal to, this one means beta 1 is equal to 0, beta 1 plus beta 2 is equal to 4, beta 2 is equal to, beta 1 plus beta 2 is equal to 4 means beta 1 is 0 means beta 2 is 4. The third coordinate is beta 1 plus beta 2 plus beta 3 is equal to 6. So this implies beta 1 is 0, beta 2 is 4 means beta 3 is equal to 2. Therefore T of u1 can be written as, T of u1 is equal to how? T of u1 is equal to beta 1 means beta 1 is 0, 0 into 1 1, beta 2 is 4 into 0 0 1 1 plus beta 3 is 2 0 0 1. So 0 into u1 plus 4 into u2 plus 2 into u3 means T of u1 can be written as a linear combination of basis elements. Okay. Next, similarly T of u2, T of u2 is what? T of 0 1 1. T of 0 1 1 is minus 1 3 4. Same procedure as in the previous element. So gamma 1 into, say, gamma 1 into 1 1 1 plus gamma 2 into 0 1 1 plus gamma 3 into 0 0 1. So this is gamma 1 plus gamma 2, gamma 1 plus gamma 2 plus gamma 3. So equating these to the corresponding ordinates, we get, say, gamma 1 is equal to minus 1, gamma 1 plus gamma 2 is equal to 3 means gamma 2 is equal to 4, and gamma 1 plus gamma 2 plus gamma 3 is equal to 4 implies gamma 3 is equal to 1. Therefore T of u2 is what? Minus 1 into u1 plus 4 into u2 plus 1 into u3. So you get second equation. Therefore T of u3 is T of 0 0 1. T of 0 0 1 is what? 0 1 3, because okay, this is equal to lambda 1 delta 1 into 1 1 1, delta 2 into 0 1 1, delta 3 into 0 0 1. So this is equal to delta 1 plus delta 2, delta 1 plus delta 2 plus delta 3. So this implies accordingly delta 1 is 0, delta 1 plus delta 2 is 1 means delta 2 is equal to 1 because delta 1 is 0, and delta 1 plus delta 2 plus delta 3 is 3 means delta 3 is equal to 2. Therefore T of u3 can be written as 0 into u1 plus 1 into u2 plus 2 into u3. We get T of u1 expression for T of u1 in terms of u1 u2 u3, T of u2 in terms of u1 u2 u3, and T of u3 in terms of u1 u2 u3. Therefore, the matrix of T can be written as M2 of T. M2 of T is what? This is 0, 4, 2. First row 0, 4, 2. Second row is minus 1, 4, 1, minus 1, 4, 1. T of U3 0, 1, 2. So, this is the matrix of the same transformation T in the set of bases U1, U2, U3. Okay, understand now? So, if they given some matrix with corresponding to some transformation T, then the matrix in the next set of bases can be obtained by first finding the linear transformation, how the linear transformation looks. Then we can obtain the matrix of the same transformation T with respect to new set of basis elements. Okay, this is one way. Okay, this is one way. So, also in the problem they were given to find the matrix of T with respect to the another set of basis elements W1, W2, W3. Here what we make is here, we find the matrix of T corresponding to W1, W2, W3 in the different method. Different method means that is by using the theorem that we have discussed now. So, the theorem says if M1 and M2 are M1 and of T, M2 of T are the matrix of T related to the different set of basis elements, then M2 of T is equal to C into M1 of T into C inverse, right. So, let us find the matrix of T related to the basis W1, W2, W3 in the another in the next method that we have that is the method by using the theorem, previous theorem, right. So, let us find this now. So, for this what you have to do, as we have to go through the same steps as in the theorem itself. So, let they were given W1 is 1, 1, 0, W2 is 1, 2, 0, W3 is 1, 2, 1. Now, let M3 of T be the matrix of T related to this basis W1, W2, W3. Okay. Now, define the transformation S from V to V by S of Vi is equal to what? Wi, where I takes the value from 1 to 3. Therefore, S of V1 is what? W1. W1 is what? 1, 1, 0. W1 given, they were 1, 1, 0. 1, 1, 0 can be written as 1 into 1, 0, 0 plus 1 into 0, 1, 0 plus 0 into 0, 0, 1. So, this is 1 into V1 plus 1 into V2 plus 0 into V3, means W1 S of V1 can be written as a linear combination of V1, V2, V3, because V1, V2, V3 is also a basis of V, standard basis. Similarly, S of V2 is W2. W2 is what? 1, 2, 0. 1, 2, 0 can be written as 1 into 1, 0, 0 plus 2 into 0, 1, 0 plus 0 into 0, 0, 1. So, this is 1 into V1 plus 2 V2 plus 0 V3. Similarly, S of V3 is W3. W3 is 1 to 1. 1 to 1 can be written as 1 into V1 plus 2 into V2 plus 1 into V3. Therefore, we have equations S of V1, S of V2, S of V3. So, therefore, the matrix of S related to the basis V1, V2, V3 is what? That I will denote it by C. C is equal to M1 of S. I write M1 because we have used the basis, we have written these using the linear combination of V1, V2, V3, first set of basis elements. So, I written, that's why by M1 of S or matrix of S related to the basis 1. So, what is the matrix? So, 1, 1, 0, 1, 1, 0, next is 1, 2, 0, 1, 2, 0, next is third one 1, 2, 1, 1, 2, 1. So, now we obtain the matrix of change of basis, which is C. So, once we obtain C, then we need to find the C inverse, because we need to have C inverse to get M3 of T. Okay. Say we know that M1 of T and M3 of T is related by M3 of T is equal to C into M1 of T into C inverse. So, here C means C here 1, 1, 1, 0, 1, 2, 0, 1, 2, 1. So, C inverse, by simple calculation you can find the inverse of C. So, this is a difficult part of problem. So, in the first stage, finding T inverse is a lengthy procedure. Finding T, the expression for T is a lengthy procedure. Here we are not going to find how the transformation looks, T looks. Okay, only we are interested in the matrix of change of basis. We can find the matrix of change of basis easily, but finding C inverse, it's a little bit time consuming task. So anyway, we need S directly I taken C inverse is this. So you substitute all the values, you get, so M3 of t is equal to M3 of 3 is equal to C into M1 of t, already we know, into S C inverse. Yes, C M1 of t into C inverse. C inverse. Okay. So that you can find to be M3 of t is -303 -724 -807. Okay. -303 -724 -807. This is M3 of t. Okay. This is the matrix of the same transformation T with respect to the set of basis elements W1, W2, W3. Okay, understand this? So you can find in either first way or this way, using the theorem or directly by finding the nature of the transformation. Okay, you can also verify that this result may holds true for already the set of the matrix which we have find out is, what is that matrix? Say we have find out, say this is the vector space we have taken. V is set of all polynomials P of x belongs to f of x such that degree of P of x is less than or equal to, say, 3. V is the vector space. T is the, say T, you define T from V to V by such that T of P of x is d by dx of P of x, d by dx of P of x. So such example we have find the matrix of T with respect to the standard basis. What is the standard basis for P of x? This is standard basis is 1 x square. So less than or equal to 3 means x cube. This is the one set of basis. Say we may call this as V1, V2, V3, V4. And also we have shown that there exists another set of basis elements for the same vector space 1 plus x, 1 plus x square, 1 plus x cube. We have find the matrix for T in the both of set of basis elements. Okay, now you can verify that the theorem, verify the above theorem that we have, the theorem which we have discussed in this class for this set of examples. You may treat this as an assignment. Okay, so you find the matrix of T with respect to this new set of bases using either the transformation T, or that is finding the transformation T, or using the theorem itself. Okay, so let's see how they are related. Again you verify the theorem. Okay, that's all for this class. Thank you.